In this chapter, we will mention properties of AC circuits that contains a pure resistor, a pure inductor, a pure capacitor, or combination of them. Let's start from some informations. For example, remember chapter 2. In chapter 2, we said instantaneous current in an AC circuit, means instantaneous value of alternating current, is calculated by maximum amount of current times sine theta. And as you remember, instead of theta we can write omega t. And instantaneous amount of voltage in an AC circuit is calculated by maximum amount of voltage times sine omega t. And in an AC circuit, current and voltage are represented by sine curves. Let's draw it. This is our coordinate plane x and y axes. Let's say this black curve, black sine curve, is curve of voltage, and this blue one is curve of current. When we draw this graph, the phase difference between two quantities, current and voltage, cannot be seen clearly. So we will change the graph to a diagram that we can comprehend better. For example, this is our x and y axis. Black curve is voltage, and let's draw black vector for voltage, and blue one is current. In this diagram, we can see the difference, phase difference between two vectors and the phase angle of the vectors. For example, for voltage, this angle is theta, and it is called phase angle. Phase angle. This angle represents the angle between vector and x-axis. But the angle between two vectors is represented by phi, and it is called phase difference angle. Now we can start our chapter. First, we will talk about AC circuit with pure resistor. When an AC circuit is connected to a pure resistor, instantaneous current, if an AC circuit contains only pure resistor, the current is shown by IR. Instantaneous current is calculated by maximum amount of current times sine omega t or theta. Instantaneous amount of voltage VR is maximum amount of voltage sine omega t or theta, we can write. When we draw sine curves of voltage and current, we will see that this is voltage, for example, it's black one, and let's say blue one is the current, is drawn like that. As you see in the graph, when voltage reaches maximum, positive maximum value, current reaches positive maximum value. When voltage reaches minimum 0.0, current reaches minimum 0.2. When voltage reaches negative maximum value, current reaches negative maximum value. This information shows us there is no phase difference between them. That means phase difference angle of the vectors, phi is 0. So we can draw phasor diagram of the vectors. Let's draw this is x-axis and this is y-axis. This is current. Always we will draw current on x-axis in this subject, IR, and this is, let's draw it right, and this is VR. As you see, there is no phase difference angle between them because they are parallel. Now let's talk about power in AC circuit with pure resistors. When we draw sine curves of current and voltage, let's say this is voltage and this one is current. We said that they reach positive maximum value, minimum point, negative maximum value at the same time, so there is no phase difference between them. Remember, power is calculated by I times V. Multiplication power is calculated by product of current and voltage. So when we draw curve of power, positive times positive will be positive, negative times negative is also positive, means power will be always positive. So we can say here average power in this circuit can be calculated by maximum amount of power over 2. Means average power in an AC circuit with pure resistor is calculated by half of maximum power. We will prove it in the next slides. Previously I said average value of power is maximum value of power over 2, half of maximum value. In this part we will prove it. In this part I will use this experiment. Actually this experiment is not included to ministry examination, but it helps us to understand better. As you see, there is a container which is filled by water and a resistor is immersed in water. There is a thermometer which is used to measure temperature of water. Two sources AC and DC are connected in parallel to resistor. Initially we will close switch 1, then direct current flows in circuit. When we measure temperature, let's say this is T1, temperature of water when DC is connected. Then we will open switch 2 and we will close, we will open switch 1, then we will close switch 2. Then AC flows in circuit, alternating current flows in circuit, and let's say temperature of water is T2 when AC source is connected. When we compare the temperature, we will see that temperature of water when DC is connected will be greater than temperature of water when AC is connected. Why? Why effect of DC is greater than effect of AC? Because DC is direct current, it is constant, so it is always affected by its maximum value. But AC is alternating current, it varies, so it cannot be affected by its maximum value always. So we can say effect of DC is greater than effect of AC. Let's continue and prove average value of power equals half of maximum value. For DC current, for DC, power is calculated by I squared R, it's constant R. For AC, power is instantaneous value, square root of instantaneous value of current times R. Then remember, in an AC circuit, instantaneous value of current is calculated by maximum value of current times sine theta. Let's place this value in the formula above. So what will be I instantaneous squared equals I maximum squared sine squared theta. Sine squared theta can be written as 1 minus cosine 2 theta over 2. Let's rewrite this equation. Power equals I instantaneous squared R. For instantaneous squared value, we will write I m squared sine power equals I m squared sine squared theta, sine squared theta times R, and power equals I maximum squared. Instead of sine squared theta, we write 1 minus cosine 2 theta over 2. 1 minus cosine 2 theta over 2 times R. Then for average value of cosine 2 theta, it is 360 and multiple of it, it will be 0. when cosine to the average value of cosine 2 theta over a complete cycle is 0, we will write our equation again. Power equals, Im squared times 1 minus 0 is 1 over 2 times r. So power means average power is I maximum squared times r, that means it is maximum power, times 1 over 2 means over 2. So we proved why average power of AC circuit equals half of maximum value. Then we said current cannot be affected by its maximum value always. Why? Because current varies. When we say dissipated power equals average power, actually they are not, IDC squared r is dissipated power because constant, and equals, what is average power? Maximum power over 2. Maximum power is Im squared r over 2. This is you see both sides have r, we can simplify them, and this is effective value, we can say, because effective current is effect of DC in AC circuits, and we can write instead of IDC, I effective squared equals Im squared over 2. We will take square root of both sides. This will be I effective equals I maximum over root of 2. This value 1 over root of 2 is 0.707. Then I effective will be 0.707 times I maximum. Also, I effective can be called as root mean squared of current. Is I effective, it is 0.707. I effective, we said, equals 0.707 times I maximum. When we multiply both sides of equation by any number, the ratio will not change. So let's multiply it by r, and let's multiply the right side by r. R times I is voltage. Here we can say V effective is 0.707. I maximum times R is V maximum. Means effective voltage is also can be calculated by 0.707 times maximum amount of voltage. In the previous part, we have mentioned the AC circuit with pure resistor. Now we will talk about AC circuit with pure inductor. In AC circuit with pure inductor, instantaneous current is represented by IL and calculated by Im sine omega t. And instantaneous value of voltage is VL, can be calculated by Vm sine omega t plus phi. That means there is phase difference between them. Why there is phase difference between current and voltage? Let's remember chapter 2. Let's consider an AC source is connected to a pure inductor. When the switch is just closed in the circuit, the current will be 0. But remember, changing current will be maximum. When the switch is just closed, EMF in inductor will be maximum. When current reaches its maximum value, there will be no change because current will be constant and EMF will be minimum. Let's draw sine curve of this information. This is our coordinate plane, x and y axis. Let's say this black one is current from 0 to positive maximum, to 0 to negative maximum, to 0 again. This is current. When we draw voltage by blue one, when current is minimum, voltage will be maximum. When current is maximum, voltage will be minimum. When current is minimum again, voltage will be maximum, then minimum again, and this is voltage. You see there is phase difference between them, and we can show this complex graph by phasor diagram. Let's say this is x-axis and this is y-axis. In the chapter, currents will be always on x-axis. Let's use blue pen for current. This is current. When current is minimum at 0, voltage will be maximum here. This is VL and this is IL. Pure inductor means a coil which has no resistance. There is no resistance in the circuit, but there is another opposition to growth of current. This opposition is called inductive reactance. Inductive reactance. Inductive reactance is represented by XL, and inductive reactance is directly proportional to frequency or angular frequency, we can say, and inductive reactance is directly proportional to coefficient of self-induction of coil. Let's prove these relations by two activities. Effect of frequency on inductive reactance. Inductive, so there is a pure inductor which is connected, let's say pure inductor, which is connected to ammeter, there is voltmeter, and there is an oscillator. Actually, this is strictly not possible, pure inductor. When switch is closed and frequency of the circuit is gradually increased, we will read value of current on ammeter decreases. Current decreases means that reactance in the circuit increases. When frequency is decreased, current increases, and XL, that means XL decreases too. Frequency is increased, XL increases. Frequency is decreased, XL decreases. That means XL directly proportional to F. In the next activity, effect of coefficient of self-induction and inductive reactance, we will insert an iron bar inside the inductor. When we insert iron bar, coefficient of self-induction of coil is increased. When we insert the bar, we will see that value of current that read from ammeter decreases. Current decreases decreasing current refers, XL increases. L increases, XL increases. So we can say that XL directly proportional to L. Now let's write. We said inductive reactance directly proportional to frequency, angular frequency, and inductive reactance directly proportional to coefficient of self-induction. By these two relations, we can write that inductive reactance can be calculated by omega L. Since omega is 2 pi F, XL will be 2 pi F L. That's right. Frequency is, remember from previous year, 1 over period. The unit of time is second. That means unit of frequency is 1 over second. And remember, L is, how can we calculate L? EMF induced equals L delta I over delta T. Okay, that means L will be EMF induced times delta T over delta I. That means coefficient of self-induction will be voltage times second over ampere. Let's place these units in the formula. XL will be, for frequency, 1 over second times, for L, coefficient of self-induction, voltage times second over A. As you see, there are two S, and we can simplify them. XL is measured in voltage over ampere. Remember, voltage equals I times R. That means R is voltage over I. Unit of R is voltage over ampere. That means voltage over ampere is also unit of resistance, and unit of resistance, as you remember, is ohm. So we can say that XL is measured in ohm. Now power in AC circuit with pure inductor. When AC source is connected to a pure inductor, the energy is stored as magnetic field in inductor, then it is released, stored, released, stored, released. So we can say that if there is no resistance, there will be no power consumed, because as you see here, positive value for current and positive value of voltage, power is positive, but here for positive value of current and negative value of voltage, power is negative, so they will simplify each other. So power for AC circuit with pure inductor can be written as no consumed. When an AC circuit contains pure capacitor, instantaneous voltage is calculated by maximum amount of voltage times sine omega t, and instantaneous amount of current can be calculated by maximum amount of current sine omega t plus phi. Again, there is phase difference between voltage and current, but there is opposition with inductor, because in inductor voltage leads current, but in this subject, in this part, current leads voltage. Why? Because let's consider a capacitor is connected to an AC source. When current is with maximum value to a capacitor, let's say current is maximum, here voltage between plates of capacitor will be 0. When capacitor starts to store energy, voltage increases, then voltage becomes maximum. At this time, remember, a fully charged capacitor behaves like open switch. There will be no current in the circuit. When we draw sine curves of voltage and current, initially voltage is minimum with black curve, let's show it, and then current maximum. Then when maximum value of voltage current is minimum, minimum value of voltage current maximum, like that, and this is current. As you see, there is phase difference between them, but current leads voltage. So when we draw phasor diagram of a circuit of vectors, here we have voltage, and here we have current. As you see, current leads voltage by 90 degrees. The phase difference between them is 90 degrees. A pure capacitor, like pure inductor, means a capacitor with no resistance. There is no resistance, but there is an opposition to growth of current, to flowing current. This opposition is called capacitive reactance. Capacitive reactance is represented by Xc, and capacitive reactance inversely proportional to frequency, and capacitive reactance inversely proportional to capacitance of capacitor. How? With these two activities we will prove it. There is a capacitor which is connected to ammeter in series, voltmeter in parallel, and to oscillator. When frequency of the oscillator is increased, we will see that current that can be written by ammeter increases too. Increasing current refers decrease in resistance, reactance in this circuit. Frequency increases, capacitive reactance decreases. That means there is inversely proportionality between capacitive reactance and frequency. In the next activity, effect of capacitance on capacitive reactance. Sorry, here frequency is constant, there is no error, there is variable capacitor. When capacitance of capacitor is increased in the circuit, we will see that current increases. Increasing current refers decreasing capacitive reactance. Capacitance increases, capacitive reactance decreases. That means there is inversely proportional between capacitive reactance and capacitance of capacitor. We said capacitive reactance behaves like resistance. That means it is also measured in ohm like inductive reactance. We said Xc inversely proportional to frequency and capacitive reactance inversely proportional to capacitance of capacitor. We can formalize this relation, so capacitive reactance will be 1 over omega c. When angular frequency equals 2 pi f, that means capacitive reactance is calculated by 1 over 2 pi f c. Remember, f is 1 over period, yes. So unit of f can be written as 1 over second. And c is, let's use black pen. C is, remember from first chapter, equals Q over V. Remember, current is amount of charge over time. So charge can be written as I times T. Let's rewrite the equation. Capacitance is I times T over V. So unit of capacitance can be written as I is current, so ampere we can write, T is second over voltage. Now let's place the units in the formula. Capacitive reactance is calculated by 1 over 2 and pi are number, there is no unit, 1 over second times ampere times second over voltage. As you see, there are 2 seconds too. We can simplify them. So Xc will be 1 over ampere over voltage. So it is voltage over ampere. Let's remember again. Voltage equals I times R, means R equals voltage over I, means volt over ampere. If resistance, the unit of resistance is volt over ampere, means ohm is volt over ampere, so we can write for Xc. Xc is measured in ohm again. Now power in AC circuit with pure capacitor, sorry, it is not true for pure capacitor. For pure capacitor, when energy is applied to a capacitor, it stores energy as electric field between its plates. Then it discharges and gives energy to circuit again. So if there is no resistance, this interchange between energy will be continuously. So if there is no resistance, there will be no dissipated energy. So we can say power in AC circuit with pure capacitor is not consumed. There is no consumed power, we can say. Now let's talk about series combination of pure resistor, pure inductor, and pure capacitor. In the picture, you see orange vectors. They are currents. Let's say this is IR, current on resistor, and this is IL, and this is IC. And the blue vectors are voltage. It is VR. Here we have VL, and there is VC, as you see. Now as I formula them, remember current here calculated by IR is maximum value of current times sine omega t, as you remember, and the voltage can be written as VR is V maximum sine omega t. These are instantaneous current and voltage in a circuit that contains only pure resistor. When we calculate instantaneous current and voltage in this part, as you remember, IL will be IL is I maximum sine omega t, and voltage can be calculated by VL is Vm sine, as you see, voltage leads current by 5 degrees, it is 90 degrees, sine omega t plus phi. When we write instantaneous value of current in a circuit that contains pure resistor, IC is, so let's write VC there. VC is aligned on x-axis, as you see, Vm sine omega t, and as you see, IC leads voltage by 5, so IC can be calculated by maximum amount of current times sine omega t plus phi, because as you see, current leads voltage. But we know in series combination all of currents are same, means IR must be equal to IL, also it must be equal to IC. So I want to rotate this diagram and I want to align all currents on x-axis. Now I can write current as, let's choose another pen. I'm not write IC because now IC is on axis, so I can write IC is I maximum sine omega t. Now as you see, all of currents become same. So, but we know in a circuit that contains pure capacitor, current leads voltage. Initially, current has greater phi, or we can write current has smaller, voltage has smaller phi. So we will change this one, means VC equals Vm sine omega t minus phi, we'll write here. Anyway, current leads voltage. Now I want to draw phasor diagram of voltage. Phasor diagram of circuit. Here we have all voltage, all currents, IR, IL, and IC. In series combination they are same. So we can draw voltage. This is VR. We draw voltage R on x-axis because there is no phase difference between current and voltage. And we know for inductor, VL leads current. This is VL. And for capacitor, VC lags behind current. So it is VC. As you see, on y-axis there are two vectors. So we will take component resultant vector of them. If VL is greater, we can draw resultant vector on y-axis as Vx. Now we have two vectors, Vx and Vr. So there is a right triangle, we can say. So we can draw total voltage of these two graphs as V total or V. So we can write relation between total voltage VR and the other vectors. Total voltage, we can consider it as hypotenuse of, let's move Vx here. Hypotenuse of this right triangle equals VR squared plus Vx squared. And total voltage will be VR squared plus Vx is VL minus Vc squared. Then tangent of this right triangle is, let's say here is theta. Tangent, so here is phi, sorry, because it is angle between voltage and current. So the angle between two vectors is phase difference angle, so it is phi. Tangent phi will be, tangent phi is opposite side over adjacent side, yes. So it is Vx over Vr. What is Vx over Vr? Vl minus Vc over Vr. And we can write cosine phi. It is, yes, adjacent side over hypotenuse Vr over V total. This is phasor diagram of voltage of series combination of RLC circuits. Now we will talk about phasor diagram of reactances in the circuit. In a circuit that contains pure resistor, pure inductor, and pure capacitor, there is resistance of resistor, there is inductive reactance of inductor, and there is capacitive reactance of capacitor. So some of them means total impedance, total reactance in the circuit is impedance. And impedance is represented by Z. We can draw phasor diagram of impedance, of phasor diagram of reactance. Here we have IR, IL, and IC. So with VR, same direction, we have R. Here we have XL. For VL there is XL, inductive reactance, and for VC there is XC. As you see, there are two vectors again on y-axis, so we will take resultant of them. If XL is greater, just we assume the resultant vector for these two vectors, XL and XC, is drawn in that direction, so it is X. When we move X here with the other vector, so there is a right triangle, so we'll draw hypotenuse. This hypotenuse is total reactance called impedance. We write the relation between impedance and the others, Z squared equals R squared plus X squared, and Z squared becomes R squared plus XL minus XC squared. Then tangent phi, where is phi? Here is phi, angle between Z and current. Tangent phi is adjacent side over neighbor side. Yes. So sorry, opposite side over neighbor side. Tangent phi for this right triangle is opposite side over adjacent side, means X over R, or we can write XL minus XC over R. And cosine phi for the triangle is adjacent side over hypotenuse, means R over Z. In series combination of RLC circuits, if XL is greater than XC, means current, means voltage leads current. That means the circuit has inductive property. Inductive property. If in the circuit XC is greater than XL, that means current leads voltage. At this time, circuit will be capacitive. When they are same, means when XL equals XC, there will be no phase difference between current and voltage, so property of circuit will be resistive. Now let's talk about power factor. Power factor is also known as cosine phi in the circuit. In series combination of RLC circuits, only there is resistance for resistor, so power is only consumed in resistor. So real power is calculated by, real power for the circuit will be IR VR. Remember, cosine phi is VR over V total. So we can say VR equals V total times cosine phi. When currents are same, we know current in series combination are same. I equals IR equals IL equals IC. So when we multiply both sides of equation by I, result of the I times VR means IR times VR is P real. It is real power consumed. And the other part, I times V total with total power, it is called P apparent times cosine phi. The ratio of real power and apparent power means cosine phi is also called power factor. It is represented by PF. It is real power over apparent power. Now, electromagnetic oscillation. In electromagnetic oscillation circuit, a fully charged capacitor is used. Firstly, a capacitor is fully charged, then connected to a pure inductor, When capacitor is connected to an inductor, capacitor discharges and starts to give its energy to inductor. When inductor stores this energy as magnetic field in it, capacitor becomes completely discharged. Then capacitor starts to charge again and inductor gives its energy to capacitor and energy is stored in capacitor as electric field. This energy interchange will be continuously if there is no resistor in resistance in the circuit. This type of circuits are used in, for example, radio transmission. An oscillator circuit, there is an inductor and there is a capacitor. When frequency of the circuit equals frequency of signal, resonance takes place. Resonance can be achieved when impedance is minimum. Impedance minimum, what does it mean? Let's remember, impedance is calculated by R squared plus X squared, means XL minus XC squared. When this part of equation is 0, impedance equals R and becomes minimum. X is 0. What does it mean? X is XL minus XC is 0. That means when XL equals XC, resonance can be achieved. What does it mean XL equals XC? Remember, XL is 2 pi FL, or let's start with it is omega L equals 1 over omega C. Let's move omega left side and L to right side by cross product rule. Omega squared equals 1 over L times C. Let's take square root of both sides. Now omega equals 1 over root of LC. We can use this equation XL equals XC if there is resonance, means frequency of oscillator equals frequency of circuit. That means this frequency is resonance frequency. And since omega equals 2 pi F, it can be written as FR equals 1 over, means resonance, linear resonance frequency is 1 over 2 pi root of coefficient of self-induction of coil and capacitance of capacitor. Quality factor of resonance circuit can be defined as ratio of angular resonance frequency and range of angular frequency, means change in angular frequency. On the graph, as you see, when resistance is small, the graph is high and sharp. That means distance between these 2 points are small. Means small resistance means change in omega is small. And when the resistance is large, as you see, the graph will be wide. For huge amount of resistance, delta omega will be high. So we can say there is directly proportionality between change in omega and R. And we know there is direct proportionality between omega, inversely proportional to omega and coefficient of self-induction. Let's remember, At the beginning of this part, we said quality factor is ratio of, quality factor is represented by QF. It is ratio of angular resonance frequency over range of frequency, range of angular frequency. We can formalize this relation. We can write change in omega is R over L. Let's write the equation. Omega R means resonance frequency is 1 over root of LC, and change in omega is R over L. Now equation becomes 1 over root of LC. Let's write them as root L times root C times R over L will be L over R. We can write instead of L root L times root L because this product gives us L2. Now this root L and root L will simplify each other, and formula will be quality factor is root L over root of C times R. So finally we write equation as 1 over R times root of L over C. Here we will talk about parallel combination of RLC circuits. All orange vectors are again current, like in series combination. This is also current IL, and this is current on capacitor. And the blue one, VR, VL, and VC. When we write formula of IR, remember, sorry, black pen, I am sine omega t, as you remember, and IL equals I am sine omega t2, and IC is, as you remember, IC is voltage and it's on my axis, it has greater phi, so I am sine omega t plus phi. We write, when write formulas of voltage, VR is, as you remember, there is no phase difference between IR and VR, so we can write Vm sine omega t. VL leads current by 5 degrees, so you write VL as Vm sine omega t plus phi, as you remember, and VC on x-axis, it has no phase angle, it actually write it as Vm sine omega t, just like that. In series combination, remember, we said all of currents are same, so we make all currents same. But in parallel combination, as you know, all of voltages are same, so we will make all voltage same. So I want to rotate. Now, as you see, we are on x-axis and we see on x-axis. I will rotate this phasor diagram and I will align VL on x-axis, as you see. That means I must change the formulas of IL and IC. Now VL on x-axis, so I will write VL as VL equals Vm sine omega t. Initially VL has greater phi, now VL also has greater phi, but I will write it as IL has smaller, like that. IL equals Im sine omega t minus phi. As you see, VL leads IL by phi. Now all of currents, VR equals Vm sine omega t, VL equals Vm sine omega t, VC equals Vm sine omega t. That means all of voltages are same. Now let's draw a phasor diagram of current. We cannot draw a phasor diagram of voltage because they are same. We cannot draw a phasor diagram of impedance because when we draw a phasor diagram of impedance, impedance will be greater than the others. But in parallel combination, we know equivalent resistance, in this chapter it is called impedance, is smaller than the others. So we cannot draw it. Just we can draw phasor diagram of current. We draw all voltage on x-axis, let's say V, VL, VR, and all that. And there is IR and 2 plus y direction, there is IC. To minus y direction, we have IL. As you see, again on y-axis there are two vectors, so you will take resultant of them. Let's assume again IC is greater, and we will draw the resultant vector of these two vectors as IX here. Now again we can move IX here, so let's draw hypotenuse of this right triangle. So I'm going to draw with another pen. Let's draw with green one. This is hypotenuse, and this will be total current. Now total current in this circuit can be calculated by square root of total current is IR squared plus IX squared. That means I total squared is IR squared plus IC minus IL squared. Then this is current and this is voltage. The angle between them is called phase difference angle, and can be shown by phi. Tangent phi will be opposite side over neighbor side, adjacent side. Yes, it is IX over IR. We can rewrite it IC minus IL over IR. And cosine phi will be adjacent side over hypotenuse, means IR over I total. Here impedance also can be calculated by V total over I total. Now let's talk about properties of the circuit. In this circuit, if IC is greater than IL, at this time remember the phasor diagram, that means current leads voltage. Current leads voltage means that the circuit is capacitive. If IL is greater than IC, that means voltage leads current. At this time the circuit is inductive. If they are same, if IL equals IC, the circuit is resistive. Please do not confuse series combination of RLC and parallel combination of it to write property of the circuit. Just consider the phasor diagram. For example, if for parallel combination IC greater than IL, let's write IC greater than IL, and here we have IR, and here we have voltage. If IC is greater, that means IX is drawn in that direction, and for IX and IR, total current is drawn in that direction. As you see, current leads voltage by phi. At this time, circuit is capacitor. Remember, AC circuit with pure capacitor. If opposite of it takes place, and means IL greater than IC, let's draw phasor diagram. To up we have IC, to down we have IX, here we have IR and voltage. If this is IL. If IL greater than IC, that means IX is drawn in direction of minus Y. So total current is drawn like that. At this time, as you see, voltage leads current by phi. Voltage leads current when, remember, in AC circuit with pure inductor, voltage leads current. So at this time, circuit is inductive. Goodbye.